guys, in this video we're going to be looking at basic trigonometry. And now if you are given a right angle triangle just like I have here with length of side A, B and C, you are asked to find a particular length of a specific side, let's say C in this case. Now this can be done using the Pythagoras theorem, which you have seen here, and c square is equal to a square plus b square. Now if you are given these two sides and you're asked to look for a, you just make a the subject in this formula here, on this equation here, and you get your answer. Now apart from knowing the length of each sides of the triangle, we can also evaluate the angle of this triangle, let's say the sine, the cosine, and the tan, or the cosecant, the secant, and the cotangent. And now, first we have to remember this SOHCAHTOA, and we are going to use this SOHCAHTOA to evaluate this right angle triangle. Now we know that from here, the sine theta of this angle here is equal to the opposite, which is this side facing the angle here, over the hypotenuse, which is the longest side, and this is given as a over c. Now we can also look for the cosine theta. Now the cosine theta following this SOHCAHTOA here is given as the adjacent over the hypotenuse. Now for this specific triangle, the specific right angle triangle here, this is our adjacent. But if your angle was being placed here, let's say the angle theta was placed here, this will be our adjacent, while this will be our opposite. But in this case, the angle was placed here, so this is our opposite and this is our adjacent. So for the cosine theta, the adjacent b is divided by the hypotenuse c. That's why we have b over c here. And for the tangent here, the tangent is given as, from here we see that it's giving us opposite over adjacent, which is opposite here over adjacent a over b. Now, but there is a trigonometric identity that goes with this opposite over adjacent, which is dividing a over c by b over c, which is the sine theta over the cos theta. And this leads us to our first trigonometric identity, which we are going to have in mind. This is a trigonometric identity that the tan theta is equal to the sine theta over the cosine theta, and this can be proven by dividing this and this, which is the sine theta over the cos theta, and you will get your tan theta a over b. Now apart from knowing the sine, cosine and the tan of a right angle triangle, we can also know the reciprocals of these angles, which is the cosecant theta, the secant theta, and the cotangent theta. Now the cosecant theta is simply the reciprocal of the sine theta. Now if the sine theta in this particular triangle is given as a over c, then the cosecant theta will be given as c over a, which is just the reciprocal of the sine theta. Same goes with the secant theta, which is the reciprocal of the cosine theta, and that is what we have seen here. And same goes with the cotangent theta, which is also the reciprocal of the tan theta. And now this is another trigonometric identity, which is the cotangent theta is equal to the cos theta over the sine theta. Now this is a second trigonometric identity which we are going to have in mind when solving any right angle triangle in trigonometry. Now there is another trigonometric identity which I would like to show us. Its trigonometric identity is popularly known as the Pythagorean identity, and we will see why it is called the Pythagorean identity in a short time. So if I square each of these sine, cosine and tangent theta here, I will have what we see here, that the sine squared theta is equal to the a square over c square. Same goes with the cosine squared theta, which is equal to b square over c square, and the tan squared theta, which is equal to a square over b square. And now if I add my sine theta and cosine theta, this is what I will get. Now my sine squared theta rather, plus my cosine squared theta is equal to a square over c square plus b square over c square. And that is what we see here. Now, since the both of them are having same on the denominator here, it's easy to add up. Now, this is what I get because of the same, you know, denominator here. So, and we can see that from the Pythagorean theorem that a square plus b square, which is what I have in my numerator here, is simply equal to c square here. So I replace that with my c square. Dividing c square by c square, I will have 1. And this is known as the Pythagorean identity. Now, this is a very easy identity to, derive from any given right angle triangle, and we are going to use a different right angle triangle to see that we can derive this particular Pythagorean identity from a different right angle triangle. Now, here we can see a right angle triangle which is labeled just two sides, the x side and here, which is the adjacent. We have the hypotenuse labeled as x and the adjacent side labeled as 1. And now we are asked to, from this particular right angle triangle, to prove the Pythagorean identity. Now, the first thing we have to put in mind is the Pythagoras theorem, which is what I've shown us. C square is equal to a square plus b square. Now, this is my a, this is my b, and this is my c. Now, you can see from here, I am looking for my a because it is not given. And evaluating this particular Pythagoras theorem, I get this, my c square, my a square will be equal to my c square minus my b square, where my b square is taken to this other side of the equation to become a negative b square. And now, since I know my c square is x square, or rather x, so I square my x, and my b square, which is here, is just 1. 1 square is 1. Now, taking the square root of both sides, I'll have that my a, which is the unknown side here, is equal to the square root of x square minus 1. And now this can lead me to this particular function here, that sine theta is equal to opposite, which is what we just got here, over the hypotenuse, which is what we see here from the SOHCAHTOA. Sine theta is equal to opposite over hypotenuse. But there's something we need to evaluate here, which is the tan theta. And tan theta is giving us the opposite over the opposite here over the adjacent. And this is what we have seen here. The opposite is what we derived from the Pythagoras theorem over the adjacent, which is 1. So my tan theta is simply equal to this. And now, from my tan theta, I can make x the subject of the equation here. And I will have that x squared first is equal to the tan square theta plus 1. That is when I square both sides. When I square both sides, the square disappears from here, and I have tan square theta here. Now, moving this negative to the right hand side, it becomes positive, leaving me with just x squared in this side of the equation. Now, taking the root of both sides, I will have that my x is equal to root 1 plus tan square theta. Now, this is another way of representing x. Now, I have a way of representing the square root of x squared minus 1, and I have a way of representing x. So I just replace it in my sine theta here, which is tan theta divided by the square root of 1 plus tan square theta. And that is what we have seen here. Now, if I further evaluate this particular function by squaring both sides, I square my sine theta to become sine square theta, square the top here to become tan square theta, and square the bottom here to become just this particular expression, 1 plus tan square theta, because the square cancels out the square root. Now, multiplying both sides, I'll have that sine square theta will be multiplied by 1 plus tan square theta, and that is equal to tan square theta. Now, opening the bracket, I'll have my sine square theta multiplied by 1 to give me sine square theta, and sine square theta multiplied by tan square theta will give me sine square theta tan square theta all equal to tan square theta here. Now if I divide through by tan square theta, I will get this. See, I have divided each of the function here by tan square theta. Now tan square theta divides here to become 1, and tan square theta cancels here, leaving me with only sine square theta. Now what about this? Sine square theta divided by tan square theta. Now we recall from this first trigonometric identity here that our tan theta is equal to sine theta over cos theta, making cos the subject here. I'll have that cos theta is equal to sine theta over tan theta. So if I make cos the subject here, cos theta will be equal to sine theta over tan theta. And that is what we have seen here. So if I square both sides, I square cos theta and I square, which is what we see here. Cos theta is equal to sine theta over tan theta. Now if I square both sides, I'll have cos square theta will be equal to sine square theta over tan square theta. So this is what I have here, that my sine square theta over my tan square theta has to be equal to my cos square theta. And we can see that this is another way of proving the Pythagorean identity.